Okay, and we have a short presentation as per the requirements in the documents.
Yeah, just please confirm that you can see the presentation really well.
Okay, thank you. Okay, so we are team 152nd Poly rocket with our rocket R6 ITER, and we are coming to Spaceport America Cup 2024. I would like to show you our progress so far with our rocket. And starting, we'd like to make some overview of the entire rocket. The rocket is divided into 5 sections. The first one is aerostructure. It is basically how the rocket is kept together and how it is aerodynamically stable. The second subsystem is the recovery subsystem. It is a part that ensures that we come back to the ground after a successful flight without any damage, of course. The third system is the payload subsystem. This is the main goal of our rocket, and this year it is collecting data on
Vibration profiles of the flight of the rocket throughout the whole flight profile, so that we can try to manage and maybe cooperate with the data of the vibrations being propelled with the rocket to a bigger rocket such as SpaceX maybe, so that it could be a test platform, a test bed of some sort for further analysis of, for example, CubeSat missions.
Another subsystem is the electronic subsystem. This is the main brain of our rocket. We use wireless communication, both long range and short range. Long range to communicate with at greater distances to remotely control our rocket and the filling process, and short range to communicate between our sub-modules inside the rocket. It also controls the filling process of the oxidizer tank inside the rocket. The last system is the propulsion system. This is, in our case, a hybrid rocket motor, SROT M classification, I think, but I will explain it up later when we come to it. Okay, this is a screenshot of the open rocket simulation of our rocket. As you can see, it has 378 centimeters. Which is, I actually don't.
It's going to be hard to convert to imperial,
yeah. But at least on the fly. It is available, of course, in the technical report in imperial units. And the apogee is 3,554 meters with a maximum velocity of 247 meters per second and maximum acceleration of around 7 Gs. Okay, the stability is 1.74 calibers, so it is within the required values. The mission concept of the operation for R6 ITER rocket is, of course, when we come to the Spaceport America Cup, we have to assemble our rocket. We need to do pre-flight operations. These entails all tests, all checkups required for a safe flight. When we are ready, we arm the recovery system and begin the filling procedure. This means transferring the nitrous oxide, in our case, from the external oxidizer tank to the internal tank inside the rocket. Then we proceed to launch operations. This means a launch procedure where we once again ensure that everything is going on all right. We begin the countdown and the rocket lifts off the path. The engine works for about 10 to 11 seconds. Then we have burnout and free lift. The initial deployment of the recovery system, the pilot parachute, is at apogee. Then the main deployment is at 300 meters, and the rocket falls down to the ground on the main parachute, where we recover it, disarm it, log the altitude from the telemetron computer, and bring it back to the tent area for inspection. Okay, now I'd like to present some details about our subsystems. I'd like to invite the electronics team lead, and he will tell a bit more about the electronic subsystem in our rocket.
So first of all, in our rocket we have 6 submodules. They are all wirelessly connected with the spinal network. First module is frontal tube module. This is responsible for calculating speed, altitude, and predicting apogee. Second one is recovery camera for monitoring deployment of recovery system. We also have payload electronic onboard computer, which is controlling any process inside the rocket and during the mission. We have vent valve, which is responsible for lowering the pressure inside the tank and performing an abort. We also have main valve, which is responsible for putting oxidizer into the combustion chamber. And we are using LoRa communication to communicate with our ground station, and using ESP-NAL network inside our rockets gives us opportunity to add additional submodules if they are needed. And the most important I think module in our rocket is main computer. And in main computer we also have commercial off-the-shelf computers. This is telemetron, which is primary for our recovery system and telemetry. And as a redundant, we have Easy Mini. And also onboard computer, I have 3 boards. They are developed by us. First is power delivery board, which provides redundant power for our computer. We also have main communication board, which is like main from broadcasting in ESP-NAL, which is calculating whole telemetry and communicating with ground station. And the last board is recovery control board, which provides the arming, data, and controlling whole recovery system.
Thank you very much. The next system of our rocket is the aerostructure subsystem, and I'd like to invite Dominic, which is the lead of the aerostructure team.
Thanks. Hello. So about the aerostructure, so as you probably can imagine, we're the subsystem that holds everything together. We use carbon epoxy and glass epoxy composites for the body tubes and other parts. Basically, we use for the body tubes, we use simple methods such as hand layup, and we use the aluminium tubes as positive molds for the composite. For more advanced shapes such as the nose cone, the fins, or the end cone, we use more, let's say, sophisticated methods to obtain some more complicated shape. For the nose cone, we use split negative mold with a vacuum bag on the inside to keep the pressure. For the fins, we've made some advancements since last year. We now use a sandwich of carbon epoxy as a facing and PVC foam as the core. We also ensured to test it thoroughly to find out the parameters, the mechanical parameters, and so on of the sandwich. With the end cone, we use a 3D printed positive mold, which we sand and to obtain given surface roughness, and then we use a clear coat and some separating agent. Yeah, basically that's it. We also have, of course, the joints in our rocket. We use 2 inseparable joints. These are the truss frames on the pressure vessel, the fuel tank of our rocket. This is the one on the top. We have two of those. They are mounted to the pressure, the oxidizer tank, and then are screwed to the body tubes on the bottom and on the top of the fuel tank. We also use the Radax module, which is used to join the avionics body tube and the recovery body tube. It is glued to the two respective body tubes, and we use some bolts to secure it. We of course have the only sliding joint in our rocket, which is used for separation of the nose cone. It is of course per the DTEG 1.5 calibers long. I'm sorry, 1 caliber long at least, protruding from the body tube. And we also glue it to the to the nose cone, and it is then separated in flight. Thank you.
Okay, thank you very much. The next subsystem is the hybrid rocket motor, the propulsion subsystem, and I'd like to invite our two team leaders of the propulsion subsystem, Miłosz and Dominik.
We have our hybrid motor engine with serial number C, and it has total impulse in range 10,000 and average thrust 936 newtons as it is presented on the picture. You can see our engine on this beautiful table. There's even more beautiful components of the whole engine. To machine all elements, maybe not all elements, but most of them, we used aluminum alloy 6082T6 because of properties of this material. There is a combustion chamber made from this aluminum alloy. There is also oxidizer tank with two valves. I can hold it, I guess. With two valves, ball valve, main valve, and solenoid valve, vent valve. So this is it. On this table, we also have our graphic nozzle in the aluminum casing. Of course, we performed all necessary tests that are required in the regulating of the competition. And now my colleague Dominik will explain our test and present results of them.
So of course, firstly we performed hydrostatic test of all non-CATS pressure vessels and hydraulics. All of them was performed successfully because, as we can see, modules still exists. For oxidizer tank, we used about 1.5 of the work pressure, and test lasted about 2 hours, which is far longer than 2 times operating time. And for combustion chamber, we use 60 seconds. Which is in the worst case 5 times longer than maximum operating time, and pressure of 60 atmospheres, which is of course 2 times operating pressure. After that, we were able to perform hydrostatic fire test. Results was shown in a technical report, and you can see them on the board. Looks pretty unstable, but we perceive that is because of our measuring system, and because of we got much higher frame rate, and we got this data is just better than previously, and this is made it look kind of bad. Pressure was a little higher than we expected, but it's still safe, and still engine is performed as well as we expected. But that's what not only test we performed, we also performed test of the COTS valve. We tested how they operating with electronic systems, And for main valve, which is made by just called ball valve, we test how it's open with higher pressure than we expect, because we expect it to open at maximum 56 atmospheres, and we tested how it's open on 90 atmospheres pressure, and it performed well. We got nothing to worry about. And last test was test of igniters. We ignite 10 of them, and all of them worked for the same amount of time. One of them did not ignite because of lack of gunpowder, which was a manufacturing error, and it's not something that we should be worried about. It was just probably something that the person who made it missed, or we just, I don't know, but all igniters performed well, although not on this one.
Okay, I think that's all from the propulsion team. Thank you very much.
Thank you.
And the next subsystem is the recovery subsystem, and I'd like to invite my friend here, the recovery subsystem leader.
Hi, the recovery procedure has two stages. The first one takes place near the apogee, and the nose cone is ejected by a pneumatic system. In this system we have a pressure tank, it's cuts, and the pipes, steel welded pipes that we have tested. We've performed a hydrostatic test at 2 times of working time and 1.5 working pressure, and it went fine. Next we have 2 solenoid valves which are connected above to remain redundancy of the system. The first stage ejects also the drogue parachute. Our working gas is atmospheric air that we fill into this tank by using a hand pump to remain waste-free and costs or lower the costs. Okay, so the second stage takes place on about 1,200 feet, and we use our thread line cutters that we call separators. It's some kind of pins with black powder inside. When it's time, the black powder explodes and pins release the main parachute from the rocket body. The parachutes are manufactured and designed by the team. We have sewing machines, we've made them, we've tested the strength of materials with static tensile test, and we have measured a drag coefficient of pilot parachute, drogue parachute. And that's all.
Okay, thank you very much. And the next subsystem is the payload subsystem, which is the main goal of our rocket. And I'd like to invite my friend here to present.
Hello, this slide is about payload subsystem. It is non-deployable. It weighs 4 kilograms or 8.8 pounds. It has a structure of CubeSat 3U, and its goal is to measure vibrations. We are going to measure vibrations by doing acceleration measurements and by later calculating the Fourier transform to calculate power spectral density and GRMS, or G root mean square, of our rocket. We use 2 types of sensors. One type of sensors are the industrial sensors screwed to the frame of the payload, and the second one is the much cheaper electronic sensor mounted directly on the PCB, and we are going to compare how cheap sensors performs comparing to
to industrial ones. And also we want to know the vibration profile of our rocket and compare it to the bigger rockets like to the SpaceX orbital rockets. Currently the system is built and it is being tested on the vibration exciter which we have on our university. Thank you.
Thank you also. And the last submodule is the ground support subsystem, and I'd like to invite my friend Łukasz.
Hello. So, in the ground support subsystems, we have launch rail, which consists of 12-meter mast, which ensure to safe start of our rocket. We then have a filling system, and to fill our oxidizer tank, we use two solenoid valves and stainless steel pipes. Then we have two scales, thanks to which we know how much oxidizer we have in our tank and in the rocket. And then we have a vision enhancement system, thanks to which we have vision and in the launch pad at all time while we are filling the rocket and then start it. So we have on this this slide we have RP and ID diagram of the filling system of our rocket. So that's it. Thank you.
Thank you very much. And these are all our modules. And now, do you have any questions? You are welcome to ask them now.
Okay, I just want to confirm that you've already done a static run on your motor?
Yes, we've done it on the 28th of March this year.
Yeah, I briefly remember that. You've already done all your ejection tests and everything, ground tests?
Yes, as of now,
to make sure that
multiple tests of ejection and also line cutter tests, and everything works fine.
Yeah, the first stage and the second stage of the recovery system have been fully tested. Both we tried using on-ground testing as well as for the parachutes. We used a high tower near our location that allowed us to test the deployment of the parachutes in the air.
Okay. Have you flown this rocket or not? You're waiting for New Mexico.
Well, this particular rocket we have not flown yet. We are waiting for New Mexico, but we have flown very similar rockets in the past. Our previous rocket, the R5, well, it was a bit different in all modules. The recovery module was completely different, but the previous recovery module was also less tested, and we were less sure that it will work. This one is improved and much better.
Yeah, it's important to mention that the project of PolyRocket is some kind of a iterative project. It's our 7th rocket that we developed for using hybrid motors for different competitions, for example for Spaceport America, but as well for European Rocketry Challenge. And last year with the R5 we had a successful launch as well as recovery.
Okay. Yeah, it's not a super requirement. I was just wondering whether you'd done it just so we knew any additional data from an actual flight test. Other than that, the rocket looks real good to me. I mean, your engineering looks fine. Looks like you've got all the bases covered for a good flight. You've got a good motor. You've already done your recovery tests, which is pretty much the main item for safety and stuff. What's your altitude on this? 10,000 or 30?
10,000.
I think it's 10, isn't it? Okay, 10,000. Yeah. Because I have two sets of teams. Some are doing 10, some are doing 30. So so just trying to remember which one you are. So Let me see. Um, I don't, see any other issues. Your launch pad, I know that was kind of more a stick drawing of the launch pad itself. Uh, how are you, is that just on the ground, or do you have stakes? Do you have guy wires or something like that to hold it in place?
The whole launch pad is on a tripod of sorts with regulated height above the ground, and it also is kept stable using steel wires that are just nailed to the ground around the launch pad itself.
Yeah, as it
Oh,
being an excessive length of 12 meters for us, we have three sets
yeah.
of retention steel wires that are on different heights of the launch rail itself.
Yeah, just want to make sure because you've already been there, but you know out in the desert when the wind gets going, it gets going. So
Yes.
so we want to make sure it's
Yeah, and
in there good.
if the wind would be excessive, we can make the launch rail itself a bit smaller by, for example, 1.5 meters, which is around three and a something, 3 and a bit foot.
Yeah,
Yeah, it's also
yeah,
regarding the launch rail. Is it important to mention that it's the same launch rail we used last year, and it even survived some call the devil. I don't remember.
Dust devil.
Yeah, dust devil.
It,
It survived.
a dust devil went right through it, and it made no impression on it.
Yeah.
yeah. I know dust devils very well. Um, okay. Have you pre-ordered your nitrogen?
Could you repeat, please?
Have you?
I think we have problems with the internet again.
You're still under the oxide.
Okay, we had a bit of a problem with the Wi-Fi here. Could you repeat last 20 seconds for us?
Yeah, I'm just wondering if you'd ordered your nitrous oxide yet.
We declared to our flyer of record that we will take 2 bottles of nitrous oxide and
Yeah. The provider is Thomas that we have with us here.
yes,
Exactly. As our flyer record.
It's difficult wearing 2 hats, but I have nitrous oxide.
Okay, as long as you got your nitrous taken care of, that's the important bit, because most of the other teams are ordering it and getting it delivered. So I just want to make sure that you already had it set up, because it's a little too late there if you had not had a source of nitrous. So other than that, I will send you a layout drawing of the launch site so that you know have where you're going to be and where your control station is at in relationship to everything else. So you ought to be able to see that, make sure that you understand what your view of the rocket's going to be for filling and stuff like that. Okay.
okay.
And where it's at in the okay. Let's see. I think that's about it. I
Okay.
don't think there's.
I have a question. If you're done, Paul?
Did you? Oh, there was one other thing. Let me look to make sure. There was one other thing I needed to check. Let's see. Have you contacted the ESRA guys in charge of your radios? Because I know in your report you said that your transmitters and receivers are over 200 milliwatts.
Yes, we've sent the declaration via the Google Forms.
station? Yeah, okay. Okay, just want to make sure that was cleared up too. Other than that, I don't have anything else, so you can go ahead and Thomas.
Okay. On your drawing, your separators that you have, I know you have one for your main chute, you have one for your drogue chute. Do you have redundancy? Do you have a second set of each of those that are independent?
So actually, it's a bit different.
There are two of them, and they are connected in series. Oh, I can. So, here they are.
Okay. So,
They're connected.
and that answers the question.
Here's
So
the drogue parachute, and here's the main parachute.
The main frame, actually.
Main frame.
It's connected to the main frame,
Okay.
and we are using the line to make it separator, to make it redundant. So we connect to recover the part of the tender descender. We connect it to the special way to make it safe to fly. And after the separators or tender descenders, I mean, will explode, the main parachute will deploy by being.
that's fine.
Yeah.
Okay. The reason you're a separator, but you actually have separators, plural, as in more than one. So you actually have 4 separators in your rocket.
No, we have 2. The drogue parachute is deployed via the pneumatic system, and there is no separators in it.
Yeah, the drogue parachute is placed in the nose cone, so it's being deployed after the nose cone separation by the pressure from the system.
Okay, so what is your redundancy on your drogue separation?
Redundancy of drogue separator. So we have we have a pressure tank in here.
Yep.
And the pressure
Yes.
is
And
stopped by 2 solenoid valves.
Yep.
And the redundancy
Okay.
is existence.
So the redundancy of the valves. Paul, are you okay not having redundancy in the tank?
Yes,
Yeah,
I think it's fine. Because we
Well,
tested this system, and there is no
Okay,
place where the leakage.
We are actively monitoring the pressure inside the tank, and we are fine with this like 20 seconds between this launch of the rocket and the initial deployment of the recovery system.
Yeah, there will be an electric pressure sensor here.
Yeah, if
So
there
your
is not enough pressure in the bottle, the launch will automatically abort.
Okay.
So you're monitoring your tank pressure prior to launch, knowing that you have a charge in your recovery system. How do you know there's pressure in that tank when
we have a
when
pressure
it's
sensor
loaded?
in the system.
The pressure of the recovery system is a part of the telemetry that is being transmitted from the avionics system to the ground station. So we know it at all times.
Okay. So
Okay, let's back up here. Okay, so you've got 2 electronics. You've got the you have the telemetrum, and you have the was it the Easy Mini or something? You have two recovery electronics. Okay.
Yes.
Is that correct?
Yes.
Okay. What do each one of those electronics fire? Do they fire just 2 total charges?
They both can
4 total.
fire all the recovery events. They are joined together using, I think, transopters.
They are connected with the optocouplers to 2 redundant microcontrollers, and both microcontrollers are connected by OR gate, and they are sending a signal to solenoid valves.
Do you have a schematic, an electrical schematic of your recovery electronics?
Yes, we do. I just need a moment to bring it up.
I would like to look at that.
Of course,
See the concern, Paul?
Yeah. Because I'm not so much worried about the tank, unless the tank is only good for one event. Is what, do we have one charge to get a drogue out and one charge to get a main out, or do we have 2 each? We should have a main and a back.
No. The the drogue is once the drogue is deployed, the main is pulled out by the drogue, correct?
Yes.
Yes,
Okay.
but it has to be released.
So they only have to have one charge on the nose coming out, but they have one tank, and if they're monitoring the tank pressure, is controlling one solenoid valve, and the other controllers the other solenoid valve. If one of their fails, the other one would basically be opening the alternative solenoid valve, but it's on a single tank, monitoring that pressure. So I think that's actually well can wait. I don't know if that's going to be approved. I think what
Yeah, so
CO2 required to eject your.
yeah, can we clarify, maybe start from the beginning?
They're using,
Clarify how it works from the start. So from the computer, we have both the COTS altimeters, so the telemetry and the Easy Mini. They connect to our SPAD recovery board that has redundancy of all electronics that is provided there. And if either of them trigger a recovery event, we have two separate wires that go to the recovery element that has two separate boards. So we have a redundancy here also that connect to two separate solenoid valves. But due to the design of the hydraulics, if either of them open, we have a full deployment of the recovery because of the connection here. But it has been tested also. If only one of the pneumatic system deploys, it's enough to launch the nose cone out of the rocket. Then, from that, we have the drogue out. When the drogue is out, the main parachute is retained inside of the frame using the tender descenders that are already redundant, as we showed. And that is also connected to two redundant electronics also here, and then going two redundant wires to the electronics that has two redundant systems that can trigger them.
Okay. I'm fine with all of that. The only question I have, a single cylinder for.
this is not a CO2 cylinder. This is a they pump up this cylinder with air. They physically pump it up.
Okay.
So on the volume valid, we need to see what the volume of that tank is to whether it has enough air in it to perform operations. So let's say that thing fires, but it doesn't release with the first one. How are we guaranteed that it will release on the second one?
Okay, well, let's back up a second. How long is the solenoid valve open for in ejection?
After they are open,
How long is your initiation system to open the solenoid valve?
if they are opened during the injection of first stage. So they are still open,
Probably.
we are not closing them.
So a deployment command is not disabled. It says deploy, and it opens that solenoid valve, and it deploys.
Exactly.
Correct? Okay, so if the valve, and I'm using a hypothetical, if the valve doesn't open correctly and it slowly releases pressure, how quickly do both events occur? Do both valves open instantaneously at the same time? Or is there a lag time from one or the other opening?
Starting off, it's impossible because these are solenoid valves, so it's impossible for them to open partially. If they open, they just open. So it's a 0 to 1 possibility. then it's maybe you can
And
continue.
they are both open at the same time. So there is comment, and this one comment open both valves at the same time.
What is the, so you see you've done ejection tests with this already?
Yes.
Yes.
Dozen.
And do you know how much air was left in your tank when you finished those ejection tests?
Yes, because we have a sensor, pressure sensor in the bottle, in the tank. Here.
And so,
Now we have.
yeah, I understand. When you got done with your test, how much air was left in it?
Nowhere.
Or was it all gone?
All gone.
All gone.
Yeah, because
So my
yeah,
valve
because
is not closed.
yeah, the valves are not
What's
closed
your initial,
after leaving.
what's your
And-
initial pressure?
And did you fire one valve or two valves?
We fire always both valves in case one is stuck, for example, the other one still opens, it is redundant, and we release all the air. It is still connected above the valve, so it still goes to both cylinders.
But we also conducted tests with only one valve, and everything was fine.
Okay, that's,
Well,
I
understand
needed to
that.
hear that, was one
Yeah,
valve
but-
was tested, the other valve was tested, both
exactly.
valves independently had the ability to do the job, both valves together also do the job. You only have one volume of air and you use that volume of air up in your event, and there is no backup air if the chute doesn't pop. So
Well, the nose cone doesn't.
the only place where there's no redundancy is the volume of air. What is your initial tank pressure?
It's 700 psi. A little more
So
than
you have 700
725
psi, 725 psi in your cylinder.
Yes.
And your volume?
Volume is about 0.35 fluid ounces.
35 fluid ounces.
Yeah. 0.16 liter.
16. 16 liters. Okay.
Um, is the tank that you're using, okay, is that an off-the-shelf tank, or was that something that you built, or is that something that you had to go buy?
We bought it. It's able to hold about 6,000 psi. So it's.
Well, I understand how much it's supposed to hold. I'm asking, what would be the problem with putting a second tank in there?
The mass of the entire system.
But actually, it's
Mass.
yeah,
So you don't have room to put a second tank in there.
Yes, there's not enough room, and the tank itself it's kind of heavy because it
Yeah,
needs to be tough and hard.
Yeah, I understand that. Um, do you have any, try to explain this. Do you have any idea of how long it would take if you had to order another tank? How long it would take for you to get it?
I think it's about 2 weeks.
Okay. Okay, so what I'm gonna do is I'm gonna think about this, and I may talk to somebody else about it. And I will get back with you within a day or two and see if we need to do something about making sure that you have full redundancy. The issue is you have redundancy, but you don't have full redundancy. You've got redundancy all through everything, except you only have one source. You only have one source. So I need to, like I said, I think I need to talk to somebody. I understand Thomas's nervousness about this, and I tend to agree with him. But the issue is trying to see what we can do to trying to see what we need to do to get it so that we know it's redundant and safe and ready to fly. So what I need to do is I will we'll close out this call,
Okay.
and I will contact the safety guy, who's a very good friend of mine. I'll contact the safety guy, and we'll discuss this and see what we can do to see about getting you guys into a double redundancy here.
Uh, just for the way the numbers work, Paul, that cylinder has an equivalency of about 3.1 grams of black powder. That's my numbers on their ejection charge. That 725 psi that they're running through their solenoid valves is equivalent to about 3.1 grams of black powder.
Are you pressurizing this compartment, or
No,
are you pressurizing what is the release on the nose cone?
Yeah, give us a minute, because we are not. It's important to mention that we're not pressurizing the entire nose cone. Yeah.
You're just pressurizing some tubes or something?
Yeah, it's a sort of
You're pressurizing these tubes that will be a bit. Actually, we've got a test nose cone here. We just need to separate it from the rest of the bracket.
all you're trying to do is punch the nose cone out enough to get the drogue out.
Exactly. Yeah.
Yeah.
Okay.
And you're hoping it's going long enough to pull the stroke out of the deployment bag.
JP?
I said you're trying to get the nose cone out fast enough to pull it out of the deployment bag, or is the drogue loose?
The drogue is loose.
Okay,
Okay.
good.
The system itself is
So-
and we are just those tubes are put on like this. Exactly. Just on
Not this side, but
it's the other side.
yeah.
And we pump air into those tubes to push out.
Looks like
Yeah, it's important to mention that even though we have like a lot of gas for such a small volume that we need to pressurize.
Exactly.
Yep. Yeah, I see what you're doing.
Yeah. It's 3 grams of black powder is or the equivalency. I don't see a problem with that. The only thing that I'm concerned of safety wise is that there's all, and I know you're recording the pressure in that tank prior to launch. So it's that 20-second window of if something goes wrong and you lose a charge, it seeps, it leaks, whatever, then there's no redundancy to back up that one tank. So,
Yeah, I'm going to get with my safety guy, and we're going to discuss this, and we'll see what we need to do, if anything, to get you back into double redundancy here.
Okay, yeah. Thank you.
I mean, everything else, it looks great. I mean, I'm very impressed.
Yep.
Do you have any like questions for the talk with the person of safety? All it's really well documented in the technical report. It's even better than we can show or say now. So please just refer to that, or we will be open to questions also for email as always.
Okay. Yeah.
Can you hold your ejection charge canister up again so I could take a peek at it? Let me move this over to a bigger screen. Okay. No, yes. Okay, rotate it 90 degrees, another 90. Yep. Uh, uh, yes, that's good, right there. It, it, it appears in theory that if it was necessary, I don't know what your weight parameters are for the rest of your vehicle, but
I don't think it's gonna be a big deal.
no,
I think
I
it's
think
gonna
you can
affect
fit a second
the-
one in there without an issue.
Yeah, yeah. What is the weight of that tank? Do you have an idea?
Of the tank, I have no idea actually. We'll check
No,
if it's
just
written on the bottom, I think. No, it's not. I think it was half a pound, something
it's
like this.
about 100.
Half a pound.
About a pound?
Half
Half a
a pound.
pound?
Yeah.
Yeah.
You know, I don't see any big problem with that then.
Yeah. Basically, if the biggest thing that you'd have is you'd have to add redundancy on reading your pressure gauges if you separated them into two independent systems, where you'd have one tank through one solenoid valve, one tank through another solenoid valve. Rotate the one solenoid valve 90 degrees, and that would give you room to put a tank on the one side, the other solenoid valve on the other side, and get rid of part of the plumbing because you're no longer looping the two together. They would be two independent systems. It might actually reduce your weight in plumbing while increasing your weight in an added tank.
Yeah,
But
it looks a
I'm
good
not,
solution.
yeah. So I'm not telling you to do anything. I'm just saying I'm concerned.
Yeah, that's fine. Well, like I say, let me go ahead and close this out, and I will get back with you within a day or two. And then we can see where we need to go forward to make sure you're ready to fly for next month, okay?
Okay. Okay.
Okay. Keep me in the loop, Paul. Thank you very much. Bye, guys.
Thank you very much.
Yep.
Bye.
Thank you.
Bye.
Thank you very much for putting this on, and I lost them, but still have, oh, there we go.
We'll talk later.
Yep, yep. Bye.
Come back again. Bye.
Bye. Thank you.
Yeah, we'll be in touch. Oh, I guess you're gone. Hello. We'll be in touch. Say, I'll get with you in the next day or two, and we'll see what it needs to be done. Okay.
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 Thank you very much for said.
Okay, we didn't hear you, sorry. Could you repeat? Nie mam pojęcia.
Włączcie kamerę.
Widzicie, że coś chodzi za tym.
Nie, w sensie to jest świat.
Po prostu
Może gra w mistrza, ale nie
tak,
gra.
Dobra, wycisz się po prostu i tyle, zostań na tym. Dobra, dobra.
jesteśmy wyciszeni?
Ale
W sensie, dobra, czemu jeden zbiornik z ciśnieniem, gdy nie zadziała jeden zbiornik z ciśnieniem, czemu dwa nagle miały jakieś...
Chodzi mu o to,
Policzył, że jak 3 gramy prochu. Jeszcze chcesz,
generalnie chodzi o to, oni się boją o to, że podczas startu tu na tym gwincie poluzuje się i stracimy ciśnienie w układzie.
Nie będziemy
Wtedy
mieli
nie mamy
jak
redundancji.
strzelić.
Ale wtedy co im powiedzieliście, że 20 sekund nic, żeby
Ale
nie
chodzi już w powietrzu. Jak się w locie poluzuje, to mamy dupę i cała rakieta na ziemię lata.
Ale dowolna złączka może się poluzować.
Ale no to jest redundancja. Myśmy mieli dwa zbiorniki, to jest mniej redundancja, ale jak się jeden poluzuje, to drugi nie.
Ale złączka się poluzować.
Ale to spotkanie
Spieprzać na bok. To co, mam dawać drugą butlę, drugi oksydajzer?
Nie, ale to jest recovery. Nie porównuj tego, to jest recovery.
No w sensie ja się totalnie z tym nie zgadzam akurat, szczerze mówiąc.
Znaczy ja rozumiem, o co im chodzi.
Ja nie, ja
Też uważam, że to małe szanse są tego bardzo.
Moim zdaniem to jest takie pierdolenie dla pierdolenia, żeby się czegoś przypierdolić. No w sensie widać, że to ekranie, no.
Ej, ale najpierw było... Dobra, to chyba nie mamy żadnych pytań. Widziałeś, tam miałem jakieś pytanie i z tego się kurde zrobiło 20 minut.
No tak.
W ogóle, ja przekliczę, co to jest za pytanie, czy mamy redundancję na tym? No nie wiem, jak będzie nieszczelność na bulki z wypełniaczem, to też nie polecimy.
W sensie, no dobra, ale Konrad ma fair point.
Ale ich nie obchodzi, że nie polecimy. Ich obchodzi to, że jeśli polecimy, to mamy wrócić w kontrolowany sposób.
Prawda.
Recovery jest najważniejszym pod tym względem.
Dobra, no naprawdę tak. Serio, ja mam wrażenie, że to była pierdolka taka...
No słuchaj, to jest miejsce, gdzie jest 150 teamów, jak komuś spadnie na łeb, to będzie... I to są Stany, gdzie można kogoś pozwać, więc wiesz.
No ale w sensie w sumie...
To nie jest meteor, gdzie spadnie komuś na łeb rakieta i wiesz.
Czy dla nas się coś dzieje jakiegoś wielkiego? Możemy dać drugą tą butlę, mamy i tak mało.
No ale to jest takie przypierdzielenie się, to jest... No, to jest coś niemożliwego.